Right, so it's great to be here today. It's good morning, really sunny and beautiful view over there. And let me see if I can find my presentation or my computer. All right, there we go. Okay, right, so I'm James Reeves, also known as Weave Jester. I've been working with Clojure for almost 9 years now. I've written 1 or 2 libraries, and I'm currently the lead developer of Ring. I'm currently working freelance as a contractor in London, and I'll be available for hire soon. Small plug there. And the presentation is transparency through data. Right, so without any further ado, I will start. So we know in Clojure, code is data. So therefore, code must already be transparent, right? The end. Okay, so it's not actually that simple. Let's start again. What is transparency? Because we know that the secret of all good Clojure presentations is to find a word and find the dictionary definition of it and put it on slides, right? It works for Rich Hickey, it probably worked for me. So looked up transparency, and the transparency has a few definitions, but the one we're interested in is easy to perceive or detect. Okay, well, what does perceive mean? And it means come to realize or understand. Okay, quite good here. But what does understand mean? Well, I looked this up in the dictionary as well. I came with understand, perceive the intended meaning of. I've got Stack Overflow here. And Rich Hickey made it look so easy. Okay, so let's try again. Let's third attempt. That's the charm. We know that transparency is about understanding. Okay, the dictionary definition is a little bit vague. We get the impression that transparency is about understanding. And from science, we know that understanding is about predictions. So for instance, so first of all, let's have a quick break here, because we have a test. Early in the morning, I know, but I'd like everybody to join in. So f of 0 is 1, f of 1 is 2, f of 2 is 4, 3 is 8, 4 is 16, so what's f of 5? So is everybody saying 32? You're wrong, it's 31. Because, of course, the sequence is that elementary sequence, which is the number of pieces in a circle, which is divided into chords connecting endpoints. This is also known as Moses' circle problem. I mean, this is elementary stuff, right? But what this tells us is that if a prediction is wrong, then we don't understand. You said 32, the actual connection is 31. You predicted 32. The actual answer was 31. So it means that we don't understand what f is. It's not powers of 2, it was something more complicated. But even if a prediction is right, we don't necessarily understand. If I had said 1, 2, 4, 8, and you'd have guessed 16, you'd have been right, but not for the right reasons. You still wouldn't have known what f actually was. And we needed to go to f of 5 to figure out that actually the sequence was broken and f wasn't what we thought it was. So are direct predictions the only predictions we can make? So here's another sort of example. We have a bunch of numbers on the left-hand side. We have a bunch of numbers on the right-hand side. We're passing them through a computer, which turns one to the other, right? So the computer is effectively predicting the outcome. We could say that a slower computer, if we had a faster computer running the same function as a slower computer, the faster computer would effectively be predicting the output of the slower computer. But direct predictions are not the only type of prediction we can make, right? Just because this computer knows that can predict the output for every input doesn't mean it understands everything there is to know about the function. And we pass these numbers to a human brain. The human would say, well, on the left-hand side, we have the natural numbers. And on the right-hand side, we have a set of primes. So this is essentially categorizing the input and the output. And even though a computer knows all of the individual numbers, grouping them into sets, making broad predictions about the output is sometimes beyond what a computer can do. Or it's a different type of prediction. So what I like to do is I like to talk about narrow versus broad predictions. So a narrow prediction is something like the above, where we're just reversing a single list. And we're predicting that this single list, 1, 2, 3, 4, 5, when we pass it to the function reverse, we will get 5, 4, 3, 2, 1. So that's a very narrow prediction because it's only affecting one input. But we can also make a broad prediction about all inputs and all outputs. And we can say that any collection we pass into reverse will have the same number of elements as the output element, right? The count remains the same. And this is a broad prediction which affects all outputs. Okay, so what we can say from this is that code that's easy to predict is easy to understand, okay? And that means that code that's easy to predict is transparent. So when we're talking about transparency, we're talking about making predictions. And the broader predictions we can make, the more transparent the code actually is. So that leads on to the question of, okay, well, what makes code predictable? And the thing that makes code predictable is constraints. Constraints like static types, immutability, pure functions. Constraints narrow down possibilities. Unconstrained code can do anything, but constrained code provides limits. And the more limits we have, the more broad predictions we can make. Right? Static types, for instance, if we have a function that has a static type and says, okay, well, the input must be a list and the output must be a list, then we can make a broad prediction about that. We can say, well, a list must have cardinality, it must be countable. If we know the types of something, we can make more predictions we could than if we don't know the types of something. If something is a pure function, we can make the prediction that if we put in the same inputs, we get out the same outputs out. We can also make the prediction that there will be no side effects. And immutability is another form of prediction. If we have an immutable data structure and we pass it into a function, we know that function is not going to be able to change the data structure because it's immutable. Whereas if you have a mutable data structure and you pass it into a function, it could change or it could not. Okay. So suppose we want to search some text, okay, as an example. There are a few ways we can do this. Let me just put this down a second, keep my voice going. I think I'll leave the lid off that. Okay, so suppose we want to search some text, right? That's a sort of common problem probably all of us have faced in computer science. We could do it with Clojure. So Clojure is Turing complete. It's not guaranteed to halt, but we can do anything with Clojure, right? It's completely unconstrained. And we could have just a loop iterating over the text. But it could do anything. We could go into an infinite loop. It could have side effects. There's a lot of stuff we can trip up on, but it does allow us to do almost anything, right? But because it allows us to do almost anything, it's hard to look at a piece of Clojure code that's looping over some text and make predictions about what it's doing. Because if we slip up, there might be something which causes side effects, or if we mess up a conditional, it might go into an infinite loop. So another option we could use for searching text is a regular expression. So a regular expression is not Turing complete, and it's guaranteed to halt eventually. It's actually a non-deterministic finite state autonomer, which is another class of computing device. And we know that if we run a regular expression, it's only going to search the text. We know it's not going to have any side effects. We know it's always going to halt. And this is kind of why we use regular expressions, right? They're a terse way of doing a specific computation. But just because the regular expression is going to halt eventually doesn't mean it's going to halt in a reasonable amount of time. We can construct a regular expression which takes more than the lifetime of the universe to complete by having sort of multiple backtracking references. But there's a third solution to this. So there's a library developed by Google called re2/j, and that's a more constrained form of regular expression. It doesn't have things like backtracking, but it is guaranteed to halt in linear time. So if you have the user supplying a regular expression, and you don't want the user to be able to cause your machine to fall into an infinite loop, then you could use re2/j, and you're guaranteed that the regular expression will complete in the time, complete in the length of the regular expression, right? So you can be guaranteed it'll halt in a reasonable amount of time. So what we have here is we have three solutions, and we're effectively going from powerful solutions to predictable solutions, right? A closure is powerful. It can do things that regular expressions can't. It can find things like the ending bracket of a nested expression, something that regular expressions can't do. But it's not guaranteed to halt. It's not guaranteed not to have side effects, whereas the bottom option is guaranteed to halt, and it's guaranteed to halt in a reasonable amount of time. So by making something constrained, we make it predictable and transparent. And by making something powerful, we make it opaque. So this leads to a general rule. And that is, with great power comes great unpredictability. The more possibilities we have to juggle in code, the harder it is to make predictions that are both accurate and broad, right? We can make single predictions, but it's very hard to make a sort of broad system without things like types, without constraints, without immutability. And the more we constrict code, the more we restrict it, the easier it is to make predictions, the more transparent it is. So here's another quick quiz for everybody. What's the first rule of Macro Club? Yes, don't write macros. But why, right? Macros are powerful. Why aren't you writing them all the time? And that's because they have few constraints, right? A macro can do everything a function can, but it can also screw around with the evaluation order. So by adding this power in, they become much less constrained. And if we want to limit the power of our language, we want to use macros as little as we can, right? I mean, they're useful when we need them, but when we don't, we should stick to functions or something even more constrained. And this is a specific property of a more general rule called the rule of least power. So this is what Tim Berners-Lee has to say about it. He says, computer science in the 1960s to 80s spent a lot of effort making languages that were as powerful as possible. But nowadays, we have to appreciate the reasons for not picking the most powerful solution, but the least powerful solution. So ideally, we want to use languages that have the least power necessary to solve a problem. But we also don't want to shift our environment every time, right? We want to keep using the JVM, we want to keep using our environment. We don't want to keep shifting between full languages every single time. So what's the solution to this, right? How do we solve this? And the solution is domain-specific languages. So I just want a quick show of hands. How many people have programmed in Ruby? Okay, so quite a lot of people. And I did as well a few years back. And in Ruby, when people talked about DSLs, what they meant is obfuscated APIs. They meant APIs which looked pretty, but you couldn't understand what was going on behind them. But when I talk about DSLs and what DSLs really are actual domain-specific languages, right? They're actual languages with a syntax and a grammar. And in Clojure, what we mean by that is we want something which has a grammar and a structure, and we make it out of data structures. So in Clojure, we want to develop DSLs which are deliberately less powerful and not more powerful. We want DSLs that are constrained. We want DSLs that are not Turing complete. We want DSLs that are restrictive and have less power than Clojure itself. So for instance, one example of this are literal maps. So the literal map structure is actually a form of a DSL. They're a DSL for defining pure functions with a single argument and a small domain. For instance, we can define not as a map, right? So Boolean not, if we pass it true, we get false. If we get false, we pass it true. And not becomes a function because maps can be used as functions in Clojure. So we can see here the domain is what we're inputting. Codomain is what we're outputting. So by using a map, we already know the domain and the codomain. If we were using a function, that's not obvious, right? And we can't query it programmatically. Because we're using a map, we can find the domain by using keys, and we can find the codomain by using vals. So we can programmatically say, okay, well, what is the set of inputs, what is the set of outputs that we expect? And these are predictions, right? We can predict the value of valid domains, and we can predict the valid input, and we can predict a valid output. If it's not in this set here, it's not a valid input. If it's not in this set there, it's not a valid output. We can also make other predictions about this. We can say it's a Boolean to Boolean, right? Because we can just say, well, what's the type of all of the inputs? Well, it's a Boolean. What's the type of all of the outputs? It's a Boolean. Well, actually, it's Boolean or nil, so it's maybe Boolean to maybe Boolean. But we can make this prediction, right? We can make this prediction of types. We can also make the prediction that it's pure. This isn't going to have side effects. This is a function which we can run. It's not going to cause anything. It's always going to get the same answer for the same input. And we know it'll always hold, right? This isn't a Turing complete thing. There are no loops here. So we know that if we define a function using a map, that function is guaranteed to hold. So by using this literal data structure to define a function, by using a map to define a function rather than code, we get all of these predictable properties for free. So a map is more transparent than an arbitrary function. Another form of DSL in Clojure that you're probably all familiar with is destructuring. So destructuring is another form of DSL, so pulling arguments out of maps or other data structures, things like this. So we pull out keys, we can add in default values, we can also do nested structures, right? So we can have a pull values out of a vector inside of a map. And we also know that this destructuring format is pure. This is always going to complete. We can't have a destructuring syntax that will infinitely loop unless we have a data structure which loops. And because in Clojure immutable data structures can't be recursive, we'd probably need to go to some weird library in order to actually screw this up. As long as we're using the immutable data structures that Clojure comes with, we know that this will always hold. And we know that it's pure. We know that it will always get out the same values for the same immutable data structure. If we pass the same immutable data structure in, it's always going to map the same values out. So destructuring is a DSL that is not Turing complete. It's very limited in scope, but that limitation makes it very predictable. we can actually look at any destructuring data structure and figure out exactly what variables it maps, right? We just need to look at the symbols. We can just do a tree search through this structure, look for the symbols, and those are the symbols that are going to be matched. Okay. So moving away from core, we have another set of things that are often DSLs, and that's when we're doing routing. Routing web requests specifically. So Compojure is a library, I think, that was mentioned before that I wrote a few years ago. I'm still maintaining it. But whilst Compojure allows for you to define routes very concisely, and whilst it's a very powerful routing mechanism because each macro results in a function, and it's all built around function composition, it also means it's very opaque. Once you've built up this chain of functions using Compojure, it's very difficult to work out what routes you have available, right? The moment it's built up, it becomes opaque. So what we have, again, is something that's powerful but opaque, and I've been working on recently another library called Ataraxy. So Ataraxy isn't out yet. There is a snapshot version. It's coming up to 0.1 at 1.0. Ataraxy actually means a state of serene calmness. So it sort of follows on from Compojure as being even calmer. There are other routing libraries like Biddy, developed by Malcolm and Juck's team. I know more about Ataraxy because I wrote it, so that's what I'm going to talk about here, and it's my presentation, so I can do what I want. And there's also a one-to-one mapping between Compojure and Ataraxy, right? We can, instead of a context here, we can use this. So you can kind of see how these things are very similar, how they have the same structure and how they do the same things. Because one of the goals of Compojure was to not just match, but also destructure. So we're not just matching user UUID, but we're also pulling UUID or UID out of this route, right? So we're both matching and destructuring it. And Ataraxy does the same thing, where we're matching and destructuring. We're matching, destructuring, and then we're pulling out this thing into a final result, which in this case is just a keyword vector. With Ataraxy, we can ask general questions and get back broad predictions about what's going on. So in Ataraxy, we can say, well, how many routes are using get, right? We can say how many routes go into /user, or how many routes begin with /user, how many routes use query parameters. And because Ataraxy has general destructuring, we can also ask more complicated things like how many routes use the session, right? What are the logged in routes compared to the logged out routes? And because we can ask questions about this, because we can predict the results, using this data structure is much more transparent than using functions as Compojure does. Another example of a DSL is Yada. So I haven't used Yada. I have looked into it. I've read some of the blog articles that Malcolm has wrote on it. But Malcolm's the guy to ask about it. So if you've got any question about that, feel free to bother him as much as you like. Another place where DSLs are often used is in queries. So in Datomic has a data structure which defines a pull syntax. The pull syntax gives us a way of pulling out the data from the database that we need. So this is an example I've just pulled directly from the Datomic website, and it's saying we want all release media, we want to get the top 10 tracks, and we want to get the track name and the artist name. And if you feed this into Datomic, it will come back with a data structure with just the information we want, all as one thing. And this is actually very similar to GraphQL, which is another form of DSL. It's not Clojure-based, but it has very broad similar ideas. There's actually a Clojure implementation called Lacinia, which is developed by Walmart Labs, and that's a pure Clojure implementation of GraphQL. I don't think GraphQL is Turing complete, because if it was, people could give you a GraphQL query which effectively crashes your server, right? But I couldn't find any information explicitly saying it wasn't Turing complete. So that's kind of a guess. I'm guessing that GraphQL is a limited, non-Turing complete, effectively data-driven DSL. Another place where we can use DSLs is in frameworks, where we can define the structure of an application using data. And this is something I've been doing a fair bit recently because I've been working on Integrant. Last night I was talking about this and somebody also mentioned Reframe, which I should make mention of, but I've never actually used Reframe. I know very little about it, so I'm just going to mention it here and ask people to check it out before quietly pretending that I never actually said it at all. So going back to Integrant, what Integrant does is if we imagine that the code base is a tree. So we can think of the main method as being the root of the tree, and then we branch out to more and more specific and more numerous functions at the outer edge, at the branches of our tree, right? And all software kind of follows this pattern. I mean, that's why we call it an abstract syntax tree, right? We're going from the root to more and more specific functions. And a library is effectively like a reusable branch of the tree we can use. Whereas a framework is more like the trunk of the tree. And this is a definition I'm shamelessly stealing from Luc van der Hart, who mentioned this at Clojure X. He was saying that frameworks are effectively like replacing the trunk of the tree, whereas libraries are like replacing the leaves or the branches of a tree. And what Integrant does is it's a framework, so it replaces the trunk of the tree. And it essentially drains the code out from the trunk and puts it into multi-methods. And the structure itself is defined just using data. So in practice, this looks something like this. So this is some normal code. We have a database, we have a handler, we have an adapter, and we have some configuration. So the database is configured using a URL. The handler actually references a database, and the adapter has this port. We also have these dependencies between these different pieces, right? So the handler depends on the database, and the adapter depends on the handler. And this is Clojure code that's probably similar to stuff you've seen or have written yourselves. And this is the structure of our application defined using code. But we can define it using data by pulling out the parts that need to be defined using code and leaving behind the configuration and the dependencies. So the equivalent integrant result, or the equivalent integrant syntax that says the same thing as this, is this. So in place of the vars we have keys in a map. And in place of these arguments, like port 80, we have values in the values of the map. And then in place of the dependencies between the individual components, we have these refs. So we can see that this has the same structure as this code, but it's all done using data, right? We have the same configuration data, and then we have the same dependencies. So the handler depends on the database connection, and the adapter depends on the handler. So it's effectively pulling out the structure and the configuration out from the code. And Integrant pulls back in the code by using multi-methods which dispatch off the keys. I explain Integrant in more detail in another talk, which is online. I can give you the URL afterwards. But for now, let's move on. And let's move on to building your own DSL. So I've talked about examples of DSLs which other people have written, but how do you actually do this in your own code, right? Because assume that you've bought into my argument that we need to go for less powerful things. How do you make things less powerful? And it turns out that building your own DSL is actually pretty tough. Won't sugarcoat it, it's actually something really hard. Because finding a good abstraction is hard enough, right? We're actually writing an API that makes sense, that's concise, that's easily testable. That's pretty tough. And writing a good language is harder still. This isn't easy. But good news, DSLs accumulate over time, right? Even though DSLs are hard to write, once we've got a DSL, once we've got something useful like destructuring or routing, it's not going to go away. We can only improve upon it. So we do have this accretion of good ideas. And I also want to share a few rules of thumb with you that I've found useful for creating constrained DSLs in Clojure. So the first one I've kind of touched on already. And that is to avoid loops and recursion. Because any Turing-complete language can simulate any other. If our DSL is just as complicated as our base language, it kind of defeats the point, right? We want something that's more constrained than the base language, otherwise we might as well just use Clojure for it. And if we make our DSL Turing-complete, it's equivalent to the base language. Anything we could write in our DSL, we could write in Clojure. And avoiding loops and recursion in DSLs is the easiest way to avoid Turing completeness, because we know that if it cannot repeat, it's not Turing complete. So we want to avoid loops and recursion. And all of the DSLs I've shown don't have a way of doing loops or recursion. They're just something which has a finite runtime. We can also look for areas where we're doing matching or destructuring. So we've seen that with routing, we've seen that with Yada, we've seen that with Clojure's own destructuring syntax. So for instance, with Ataraxy, Ataraxy both matches and destructures at the same time. And often these things combine together. Clojure doesn't combine matching and destructuring, it just has destructuring. When you're developing DSLs to match, often you want to pull data out of the things you're matching, right? Matching and destructuring tend to go hand in hand. So often you'll get DSLs which both match and both destructure. The other thing that we want to look for, as well as areas where we're matching and destructuring stuff, is for static structure. If we have places where we have a static set of dependencies between things, where we can say, okay, well, this isn't going to change. We know at compile time that the database is going to depend, or the handler is going to depend on the database, and the adapter is going to depend on the handler. Or maybe we have got set up a bunch of streams at compile time. So again, this is an integrant is an example of this, where we have a static structure, we can build a DSL around it. And this doesn't necessarily have to be the structure of your whole application. It could be a structure of your sub-application, right? A series of rules that you know are static at compile time. And Yada is kind of an example of this, right? It sets up a structure of the resource and of a bunch of outputs, content types which you can produce. And this static structure can be effectively represented as data. As well as looking for static structure, another thing we can do is make use of namespace keywords, because namespace keywords are great. The more I use Clojure, the more I'm using namespace keywords. I'm not aware of any other language, and maybe people can correct me on this, but Clojure has the richest keyword syntax of any language I'm aware of. Because not only do we have keywords, we also have namespaces for keywords, and we also have an inheritance tree for keywords. So we can define keywords in terms of other keywords. And this is something that I didn't use for like the first 7 years of using Clojure. Then recently, in the past 2 years, I've written multiple projects which use keyword inheritance a lot. And integrant is one of these things. In integrant, we can say that the ring adapter key, or the ring jetty adapter key, inherits from the ring adapter key. So then we can search our configuration. We can say, are there any keys that inherit from a ring adapter? Or are there any keys that inherit from server or queue? So we can talk about, we can use them as effectively definitions for dictionaries, right? Because if the syntax of your language, if the syntax of your DSL is equivalent to grammar in English or in a natural language, then keywords are analogous to the words in a sentence, right? And that makes it important, right? Keywords are the things that bind together the rest of our DSLs. So make liberal use of them. The other thing to do is make use of different data types. Clojure has a lot of different data types, more than most languages. It not only has maps, but it also has things like sets. We distinguish between lists and vectors. We have ratios and integers and floats and big integers and all sorts of things like that. And by making use of different data types, we can effectively make our grammar both more consistent with Clojure and also take some shortcuts. So Ataraxy takes this approach, where Ataraxy uses the type of the data to determine what it does. So in Ataraxy, keywords are request methods, symbols are path parameters, raw strings are static paths, sets are query parameters, maps are request destructuring, and if you want to combine these rules, use a vector. And this means that the grammar effectively becomes like a case statement, right? We dispatch on the type, and by dispatching on the type, we can avoid a lot of the problems with more complicated grammar. But when we do have complicated grammar, we actually have a tool for that as well. If you can't use a simple case statement over types to define your static, to define your DSL, we actually have Clojure spec. So Clojure spec has been used for validation. So you've probably seen, actually, who here has heard of Clojure spec? Pretty much everyone, which is good. And who here is actually using it? Okay, it's good. Who here is using it for anything other than validation? Okay, so there are a few people. Okay, that's good. We're making progress here because Clojure spec can destructure a data structure, right? It's effectively like a parser for languages written using Clojure data structures. And if you're not bored about hearing about Ataraxy, I actually use spec to parse some of the more complicated parts of Ataraxy's syntax. Okay, and that's the end of the presentation. Are there any questions?
Okay, that was a lot of build-up, but my question is good. What did you mean by keyword inheritance?
So keywords can be derived from other keywords. Clojure has inheritance in the same way that object-oriented programming has inheritance between classes, but in Clojure, it's inheritance between keywords. So any namespace keyword can be derived from any other namespace keyword, and it's multiple inheritance. So, for instance, you can have a keyword which is, let's say, server.http /jetty, right, to define a HTTP server. You could derive that from a keyword called server/HTTP. And because Jetty is a synchronous HTTP server, you could also derive that from a keyword called server/synchronous. So by deriving it from different keywords, we effectively build up a thesaurus or a dictionary, right? A definition for the keyword. And we can say, find me all servers in a map, or find me all servers that are synchronous in a map, right? So it uses the derive key, clojure.core/derive. I think there's more information under multi-methods. So if you look at multi-methods on the Clojure website, it will tell you about keyword inheritance.
Any other questions?
Can I start from here?
No, I think it's better if we record.
Okay. So if I understood your message correctly, you talked earlier in your presentation about limiting your domain-specific language to not looping, not being fully Turing complete, and so there's something to be said for that. On the other hand, it's dependent on the problem you're tackling. So if your problem is a problem that's in essence Turing complete, then you need a domain-specific language which is Turing complete. But later, I heard you say that you were talking about more complex grammars. So I want to know how do you reconcile the idea of having a complex grammar with a simple language? So the grammar in some sense should express your problem, and if your problem has a more complex nature, then can be expressed in a more limited language than a Turing complete one. How do you reconcile these things?
Well, if you're developing something and you need Turing completeness, you kind of want an API rather than a DSL, right? Because if you're using an API over Clojure, well, Clojure is already Turing complete, and you are not, or you get other, it's both easier to write an API, and also you get the benefit of familiarity, effectively. So you can use tools that Clojure already has on an API that you can't use on a DSL. The other part of the question is that you can have very complicated languages, or you can have non-trivial languages that are not necessarily Turing complete, right? The regular expressions themselves are actually pretty complicated, but they're not Turing complete, right? If we wanted to parse a regular expression, it would be hard to do without another kind of parser, effectively. We can't just kind of dispatch on the type. So you can have pretty complicated languages that are not Turing complete, but just have like a broad range of things. So rather than having depth, they have breadth, right? They're essentially very simple, but they have a lot of stuff they're doing, whereas any Turing complete language, I mean, Turing complete languages can be pretty simple, right? They can have like, you only need 6 instructions to create a Turing complete language. So you can have a very simple but very sort of deep Turing complete language, which can do a lot of things. Or you can have a very broad but very limited DSL that's not Turing complete. Does that go some way to answering your question? Okay.
Okay, we have time for one more question. If not, oh, hi.
Yeah. You also named static typing as a way to make your program more predictable.
Yes.
But Clojure is dynamically typed, and this means probably that it's more powerful, because it's more powerful means less predictable.
Yes.
What is there a tension between these?
Yes. So, like, one of the things I quite like about Clojure is it has a very wide range of power, right? You have very simple things like an immutable map, which is effectively at the lowest end of power, right? Earlier on I gave an example of defining Boolean not using an immutable map. That's probably like at the limits of the least powerful stuff in Clojure. And at the other end of the spectrum, we have macros, which are like the most powerful thing in Clojure. So Clojure has this kind of very wide range of we can use limited stuff when we need to, or we can use powerful stuff when we need to. And if you statically type your whole language, well, you're constraining your whole language. And maybe that's good in some cases, but in other cases, you actually want more power. So Clojure allows you to be limited when you need it and powerful when you need that. And if we look at the, like core.type, for instance, a static typing system for Clojure, spec is a typing system, and there's a library whose name escapes me, I think called Tensor or something like that, which does static typing over specs in a fuzzy kind of way. But yeah, so but the point about core.types is it's optional, right? If we find that the type system doesn't accommodate what we want, then we can do away with it. And essentially, static typing is a machine way of doing something we're already doing in our heads, right? When we look at a function, we're statically typing it ourselves in this kind of fuzzy static analyzer we have in our skulls. And what static typing systems do is they're a more constrained form of static typing, which follows rigorous rules, but is guaranteed to come out with a correct answer. But yeah, it constrains, and sometimes we don't want those constraints. So does that kind of answer your question? Okay.
Okay, I think we're right on time. So before we close, I have an envelope. So I'm going to try to give it to James.
Okay.
Let me see. Oh, so the award goes to Scala. No, it says Clojure. Sorry. Anyway, thanks a lot, James.
Thank you.
Sorry, so no more questions, but you can talk to him, and I think you'll be here until the evening.
Yes, I will.
Yes, so we have plenty of break in between, so stretch yourself, and please, people who are standing behind, we have spaces here, so please settle down, and we'll put some more chairs here as well. And a big round of applause to James.